Welcome to Study Loop.
Problem 8.67. We have two blocks moving towards each other on a frictionless table. They have these spring bumper things that make their collisions perfectly elastic. And what we want to know is what is the maximum potential energy that gets stored in the springs. And also we want to know what is the final speed of each block and direction. So the net momentum of this system is not zero. So when the blocks are in contact with each other, they're still going to be moving. So the potential energy is going to be the kinetic energy at the beginning minus the kinetic energy that the system still has while the blocks are moving. Now we need to know how fast they're going. So the center of mass of this is moving at some speed, and when they're stuck together, they're going to be moving at that speed, basically. So, and you can see how if you rearrange what I'm about to write, that you could get there from conservation of momentum just as easily. So we have the initial momentum of A plus the initial momentum of B divided by the sum of their masses. So you can think of this either as conservation of momentum or as asking what is the center of mass speed. They're equivalent questions. In any event, this works out to be negative 1/12 meter per second, or 0.0833. Pretend that looks like a 3 at the end there. It's not really something we're looking for, but yeah. So we need that. And then U max is just a simple matter of plugging in all of our kinetic energies. Just going to take the 1/2 out front so we don't have to keep writing it. A, B, A, initial squared, plus MB, BB, initial squared, minus their kinetic energy when they're moving together, which is an object with the combined mass of the two, moving at this center of mass speed. And so if you put the numbers into that, you get 5.21 joules. Now, there's an equation in the book that gives you the speed of each object when you have a collision like this, where one of them is stationary. But when both are moving, we need to start with this equation that relates the relative speeds before and after the collision. And of course, the conservation of momentum. So MA VA final plus MB VB final equals M A VA initial plus M B VB initial. Now you have two equations and two unknowns, and it's not terribly difficult, although it is rather tedious to work through solving all of these. So I'm not going to walk through all of that here, I don't think. It is good practice. So, you might as well do it at least once, one of those sort of things. But here we've got we end up with the final speed of A being equal to, actually, let me write this in a different order. Yeah, so we have the difference of mass between A and B times A's initial speed plus twice B's initial momentum and this is just divided by the total mass. Yeah. And then just to make sure, what I did when I was working this out is actually, you can solve this for VBF in terms of VAF. Put that in here for VBF, solve for VAF. And then once you have an expression for VAF, you can put that back in here and get VBF. And, I've done it that way. But also what you can do, and I did it that way just to check to make sure that you get the same result, is notice that there's not really anything special about A and B. So if you swap A for B everywhere in this equation, you get the equation for VBF. So let's go ahead and write that down just sort of by eye. The equation in the book that's specifically for, that should be a B, sorry, that's specifically for when one object is stationary doesn't have this symmetry. Because one of them is special, it's stationary. I mean, this equation will reduce to that, or these equations, I should say, will reduce to that if one of them has, is stationary. And, that's something you can check for yourself pretty easily. Plus B. So now the difference in masses is 8 kilograms. Here, since B is heavier, it's going to be -8. I have to remind myself that that is 2 meters per second. 2 meters per second. And now VBI is negative. So I need this minus sign here. And its mass is 10, so let's just go right ahead and call that 20 because we're multiplying it by 2 anyway. And that's a half meter per 2? No, per second. All this divided by 12 kilograms. Probably going to have to start another page for this one. So this is -16 minus 10 over 12 meters per second. And then that is 2 and 1/12, or -2 and 1/12. I'll spare you the ongoing use of fractions here by writing it as a decimal, 2.17 meters per second going to the left. Now, the BF, same story. We have the difference in masses, just the other way around. So the initial plus 2 times the initial momentum of the other one. Divided by the total mass, which is again 12 kilograms, and I'm not even going to bother writing out the symbolic version there. So if MA minus MB was -8 kilograms, then this is going to be +8 kilograms. B was initially going at -1/2 meter per second. Multiplying 2 by 2, we get 4 kilograms times another 2 meters per second. All this 12 kilograms. So we have 8 minus 4 divided by 12 meters per second, and 4, this is 4 obviously, and then 4/12 is 1/3. I'm sorry, -8 plus 4. So negative 1/3. 333 meters per second. Just look over that real quick to make sure I didn't do anything silly that I didn't then catch. Oh, no, yes, I did. This negative should not be here because this is where the 4 came from and this is where the 8 came from. So sorry about that. Anyway, so this goes off to the right at 1/3 of a meter per second. And then A goes whizzing off to the left at negative 2.17 meters per second.